Hey, what's up, AP Calculus students? Today we're looking at 5.4 modeling and optimization. So when we're talking about optimizing something, it means that we're maximizing or minimizing whatever we're looking at. So dependent on the situation. Now let's just jump into some examples because a lot of these are just difficult in the setup of it. So once you see how different models work, then you should be able to do the derivative stuff pretty easily. So for this example, it says find two numbers whose sum is 20 and product is as large as possible. So the key here, we know that we're adding them to get 20, and we know that the product is large as possible. So let's say that we have, well, let's do this first. Let's say the first number is x. Then the second number, if we know that the two numbers add up to 20, then we know that the second number is going to be 20 minus x. So let's say x is 5. Then the second number would be 20 minus 5, which is 15. And those definitely add up to 20. So this takes care of the sum part. Now the second part, it says the product is as large as possible. So we're trying to maximize this product. So we're going to multiply the two things. And we know that we'd find maximums and minimums when we do the derivative and find where the derivatives equal to 0. So let's do the derivative of this. And this is a product rule. The other way we could do it is we could have just distributed out the x's. Well, maybe we should just do that anyway. So we get 20x minus x squared. And then our derivative is 20 minus 2x. So we're trying to find out where this is equal to 0. So let's use our algebra here. I'm going to subtract our 20s. 0 minus 20 is negative 20. And then when we divide by negative 2, we end up with 10. Okay, so the two numbers are 10 and 10 to maximize the product. All right, example 2. It says a rectangle is inscribed under one arc of the sine curve. What is the largest area it can have? Give the dimension. So let's draw this out first. Let's say this is our sine arc, right? It starts at 0. It goes up and comes down. And that's half of the sine wave, right? So this is going to be, instead of 2 pi, this is going to be pi, right? If we extended it out all the way, then it would cycle through once. One period would be 2 pi. This is 0. Okay, and if we're doing an inscribed triangle, or rectangle, sorry, what it looks like is the top corners are going to touch the outsides, or touch the sine curve. Alright, so these points here. Alright, so we're looking at the area of a rectangle. Area of the rectangle is length times width, or in this case it might be better to think of it in terms of base times height. So we're going to say is, alright, let this be x, right? Then this segment on the right side would also be x length, right? Because we have symmetry. Now we have to represent the base and the height in terms of x. So the base, follow me here, the whole thing is pi. And then we're going to subtract these two x's. So what that would give us is this base length here. So 2x. Alright, our height is just going to be the height of our sine curve. So sine x. Alright, so what we're going to do is we're going to multiply these two together to get our area formula. And we're going to try to maximize this, right? So let's go ahead and do the derivative and figure out where this is equal to 0. Let's change colors one more time. So this is a product rule. U is pi minus 2x. Du is negative 2. V is sine x. dv is cosine x. Alright, so we're going to go ahead and do u dv pi minus 2x cosine x plus v du, or plus negative 2 sine x. Whoops. I'm trying to find out when this is equal to 0. Okay, so we're going to go about doing this. So we can't solve this algebraically, so what we're going to do is we're going to use the graph. Alright, so let's go grab our calculators here. Alright, so we're going to graph y equals, and we're graphing negative 2 sine x plus pi minus 2x cosine x. Okay, we're trying to find when this is equal to 0, so let's grab this. Calculate 0. Okay, so what we have here is we found the 0 and it's at 0.711. 0.711. So what we're going to do here is we're not going to round it. We're going to go ahead and store it. So press second, second quit. Whoops, second quit. I'm going to store the answer in A. So we're going to hit enter. Now that thing stored in A. That would be the excuse me, that would be the X, right? So we have to go back in and plug it into our formulas. So let's go back to our work here. So we stored that value in A. So A is approximately, now we're not going to approximate it yet. That's why we have it stored in our calculator right now, but we need to plug them in for the base and the height so we get our dimensions. All right, so when we plug it in, pi minus 2 times, since we started in A, we can put an A in there, we get 1.721. 721 for the base, and the height is going to be the sine of A, which is 0.652. 0.652. Okay, so some good calculator practice, some good setup, and talking about inscribed rectangles and other shapes is good practice as well. Okay, so make sure that once we find the thing, we also make sure we're answering the question properly. It says give dimensions, so we gotta actually give the dimensions and not just find the x value. Okay, on to the next one. An open top box is made by cutting congruent squares from the corners of a 20 by 25 sheet of tin and bending up the sides. How large should the squares be to hold as much as possible? Alright, so let's draw this thing out. It's 20 by 25. And what we're doing is cutting out squares here. And all the squares are the same. So we'll say those squares are x by x. Okay, what they're doing is they're folding this up, so we have like a box that looks like this. Alright, so we're looking at the volume. Alright, so let's represent this. So the volume, in order for us to do the volume, it's going to be base times height times, what would you say, depth, width, base times height times width. Either way, we'll be okay. So the height of our box is going to be x. Our, what we call this, width of our box would be 25 minus the two x's that we cut off, right? We cut off that part and that part from the width. And then the base, I guess you're saying here, would be 20 minus 2x, right? Because this is the 20 and we cut off two x's from the top and bottom. Okay, so when we put this all together, we can get 20 minus 2x times 25 minus 2x times x. Okay, so let's go ahead and distribute this out. It's going to be 20 times 25 is 500 minus 40x minus 50x plus 4x squared. Right, and then we still have this x here. So let's simplify this a little bit. 500, and we can, I guess, distribute the x at the same time. So we have 500x minus 40 and 50 is negative 90x squared, and then 4x cubed. We're going to do our derivative at this point. So 500x derives to 500. 90x squared becomes 180x, and then 4x cubed becomes 12x squared. And we can go ahead and start factoring this, but before we do that, let's simplify. So these are all divisible by 4, right? So 500 divided by 4. Okay, so let's factor out the 4 so it's easier to factor. This is going to be 125 minus 180 divided by 4 is 45. And then 12 divided by 4 is 3. Okay, is this factorable? Is there something that multiplies to get 3 times 125 is 375 and adds to get 45? Let's see. $25 and 15 is not going to work. 375. $5 and 75 is not going to work. What else can we choose here? Maybe we can't factor this. We're gonna have to go back and use a quadratic or go and put it in to our calculator and graph it. Yeah, I don't think we can factor it. So let's use the not the Pythagorean theorem, but the quadratic formula. So let's do A would be 3, B would be negative 45, and C would be 125. Okay, and let's put it into negative b plus or minus square root b squared minus 4ac all over 2a. Okay, so we have 45 plus square root of 45 squared minus 4 times 3 times 125, and then divided by 2 times a, which is 6. That gives us 11.31, which I think is too big. Yeah, so let's try the other one. So let's try the minus. So we get, and the reason it's too big is because we can't cut 11 from each side here for the 20, because then that would be too big. We'd be cutting through the whole box. So let's try the negative one. So it'd be 45 plus square root 45 minus 4 times 3 times 125. Oops. Oh, I forgot to square it. 45 plus square root 45 squared is 4 times 3 times 125. And then we'll divide that by 2a again. Oh, that should be a minus. 45 minus square root 45 squared minus 4 times 3 times 125. Okay, and then when we divide that by 6, we get 3.681. Oops. And this is reasonable, right? Because we can definitely cut 3.681 from here and from here and still have some left over, as well as from here and here. So this would be our answer. Okay, so yeah, the idea of optimization is not too bad. It kind of fits with our things that we were working on beforehand, but the modeling part is probably something that's going to take you some time to get used to and see how to set things up. So we're going to spend 2 days on this. We're going to do this stuff with modeling and optimization first, and then we're going to talk more about financial stuff and like business related optimization. So good work today.